I'd like to thank all the organizers for this very wonderful workshop on behalf of Rodrigo and Rafael. I would like also the opportunity to give this talk in this conference. As said, I'll talk about Moire excitons in twisted van der Waals hetero-bilayers. Okay, most of this work was done for my PhD student Giovanni. So just to put you on the same page, I belong to condensed matter theory group from Federal University of Ceará. It's northwest of Brazil. It's really, I mean, we are in the northwest, yes. I mean, it's really close to Natal. It's by car, it's 6-7 hours, depending on how fast you go. And here, the group that I'm also a member, Professor Gil is the leader, and all the rest work. I mean, me, Andre, and Milton is the one that work close in those 2D materials, plasmons, and exciton complex. So you also have for 2 + 2 years as a visiting professor, Professor Francois Peters. And just some pictures of our group. Those guys that they that do the hard work. So let's start the talk properly. So since that I'll talk about those quasi-particles, excitons, not just excitons, but Moire excitons. I'll talk a little about excitons, and after that, this additional degree of freedom concerning the twist and the 2 layers, okay? So, exciton and TMDs. So, TMDs, as you know, is a huge family, a huge 2D material family, composed more than 40 different lamellar materials, and they can be viewed as a transition metal atomos layer sandwiched by 2 chalcogen atomos layers. So spin-up coupling is too strong in this system. It has a spin valley physics and different selection rules for K and K prime values. So it's like graphene, but with spin-up coupling. Okay, and a very interesting feature for this talk is that TMDs host excitons and other different kind of complex excitons like trions, that is our charged excitons, and biexcitons. And unlike standard semiconductors, the bind energy is at least 1 order of magnitude than the conventional semiconductors. Like, for instance, in conventional semiconductors, it's KBT at 27 millielectron volt. Here, it would be like 400, 500 millielectron volt. And they can be, it seems that, we are theoretician, but it seems to be very easy to measure this in the PL experiments, okay? So, and why those TMDs host very strong bind energy excitons in comparison to the semiconductor is because it has a reduced dimensionality, reduced dielectric screening. It seems that this part is inversely proportional to the Coulomb interaction. It has a strong Coulomb interaction that in turn leads a strong excitons effect. Okay, so this I'm just talking about excitons and monolayer, and let's complicate more this system. You also can tune those excitonic properties by stacking different layers. For instance, we show in this paper in 2023, we investigate theoretically 2 TMD layers separated by a dielectric environment, and we show how those exciton properties like bind energy and exciton energy change as a function of the distance between the 2 layers, and also the dielectric constant of this dielectric slab. Okay, And we explored this for the interlayer and interlayer situation. So put another layer, make difference in your excitons properties. Another degree of freedom is twisting. I mean, slice one layer with respect to the other one. Just to say, just one slide back, that depend on the band alignment of your the two compounds, two TMDs compounds for your double layer system. It can be a type 1 or type 2 band alignment. And just to say that those type 2 band alignment has a long time life, so it's why this top got a lot of interest in this last 10 years. It's because, as you can see, electron and hole are located in different layers, and more than that, in different bands. So the recombination time is long, and it making it easier to measure this in the experiments. So the other degree of freedom that I was talking about is twisting the two layers. So the whole conference, it's about twisting system, and as you know, by twisting, we observe those Moire pattern. And if we measure that, it can be viewed as different spot with different alignments. And for each different alignment, if you, for instance, in your first principle calculations, just slice one layer with respect to the other, take this unit cell and calculate the bands. For each spots, we're going to get a bind energy and a distance between the two layers. I mean with that you're going to have a energy gap, a position-dependent energy gap, and a position-dependent interlayer distance when you map this Moire potential. Moreover, concerning the interaction between the particles, I have to say that, for instance, if you take two atoms, we just saw a very beautiful talk concerning the coupling, relaxation, but here just a naive view of that. We know those guys interact like exponential decay, and as much as the distance increase, the hoping integral go to 0, and by increasing the angle, you decrease the Moire supercell period, as I show here. Just to say that by twisting the two layers, you can tune the energy gap between the two layers. In this sense, we go to tune the properties of the electron and holes, and with this, the properties of the exon that those TMD host. Okay? So with that in mind, people has measured that, what I just mentioned. As you can see, for the profile of those the profile of the potential, that you have some hills and valleys for the different spots with the different stackings. And in 2017, this very nice paper in Size Advantage took advantage of a tight by model for maximum localized Wannier functions, tight by for cold atoms, and propose a model to directly treat Moire excitons. I mean, excitons that lives in this twist system as a quark particle. Model this with a couple of things. One of that is the energy gap difference per stacking. For instance, here A and here it's A, you go to see a minimum, here B, here it's the position of the energy gap for B and C and so on so far. Just to say that you go to have an energy modulation, and the way that you can easily see that is like one electron that is in spot A to jump for B, they should have energy sufficient to hope to jump, okay, this barrier. This is the sense. I just to say that the model that you go to use for discuss our results here, it's a very simple model to deal with a very complicated problem, okay? And moreover, I have to say that this guy here discussed also how the interlayer distance and the band gap energy change when you apply a perpendicular electric field, okay? So this is pretty much map on this potential. As you can see here, now your energy gap profile, you go position depend, as well as the interlayer distance will be position depend. I have to say that in this model, the bind energy should, in principle, also depend on the position and also the other factors like the twist angle. But most of the results that this paper and also the results that I'm going to present here, we're going to assume this as a constant, okay? And those functions, those positions dependent functions, as you can see here, depend on those F naught and F plus and F minus that in turns depend on the symmetry of the system. So here it's twisted bilayer TMDs. It has those C3 symmetry. And in this size advantage paper, they give all the parameters that are fitted, that are fitted from, I mean, after they relax, they do the linearization, plot the Hoping parameters, this distance, fit, when with this fit curve, they give those constants. I go directly use that. So I go show here results for this kind of combination for the TMDs. And as I was saying, we map this very complicated system of a twist bilayer TMDs as a honeycomb-like lattice where each spot, just go back a little, each spot here is seen as a sublattice, okay? So by doing this map, we can plot this potential profile, as I'm showing here, for 3 different kind of perpendicular electric field. And I would like to emphasize that by applying this electric field, there is a certain kind of situation that we call critical bias voltage, in which the minimum in A and B spots will be equal, you'll be at the same level, and this situation, as I go showing you results, will present a very nice excitonic band structure. So just to say that those size advantage paper took advantage of this PRA, where they proposed the static bi model for a honeycomb optical lattice using a maximum localized Wannier function. And so what they did is pretty much do the DFT calculations using the functions that this paper gave and fitting. And I'm using that, okay? And they said, I mean, they report in this paper that if you use until 3 nearest neighbor tight bi model, you can capture all the physics for the 2 lowest band. Okay? So with that in mind, I give some motivation for the exciton part, for the Moire part, and I introduce this quasi-particle called Moire excitons. Now let's go to define our Hamiltonian and start to present our results. So as I said, we have a twisted bilayer TMDs where each spot is viewed as a sublattice, and here are the first, the second, and the third nearest neighbor tight by Hoping that is given in this PRA paper, and the parameters given in the size advantage paper, okay? Where this T naught and T2 are the first and third nearest neighbor, and TA and TB are connected to this energy difference concerning to this middle point D. Okay, so this is the function that the size advantage paper gave, As you can see, it depends on this ER that, for instance, that in turns depend on B, and B is the Moire supercell constant. As you can see, if you increasing, I mean, as you go to C, just, yes, now. If you increase the twist angle, you go to decrease the Moire supercell constant, and by decreasing that, you go to increase this energy. So I want to say that you change theta, we change B, we change the energy, and at the end you change the hoping. And to show that, I show this plot here, that by changing theta, we'll decrease, I mean, by increasing theta, we decrease the Moire superlattice constant, and also go to increase the hoping. And it's linearly dependent on the bias voltage, okay? That is related to the band alignment of those two Waals. So here's those function that is like structure factors. And by diagonalize that Hamiltonian, you get those two band model. I mean, those two bands that I'm showing here for different twist angle and bias voltage. So green, blue results, you see that the two bands are gapped, but for a critical value, in the case that those VA and VB are have equal energy in the minimum, surprisingly, we close the gap and you get some Dirac-like exciton band structure for this situation. So in summary, we can tune the excitonic band structure, close the gap, and get some linear dispersion around the gamma point. And it's in energy, it's just a little shifted, okay? And moreover, by increasing, as you see the dot, dash, and solid lines, by increasing the twist angle, you go to modify the group velocity. And if you look carefully around here, the crossing point, the gamma point, you go to see that the certain iso energy is asymmetric. So with that in mind, once that I want to first investigate the dynamics of those Moire excitons, we wrote the tight by Hamiltonian as a function of the Pauli matrix. So that Hamiltonian that I just wrote a few slides before can be written like that, where this SK vector has those components, and this T plus is given related to the TA and TB. And our pseudo spinor in a time further can be written as a multiplication of these two exponential. See that this part commutate with this part, so it's why you can split it, okay? So there is no approximation here, since that these two parts commute, and I need to set the initial wave packet that I set as a Gaussian, circularly symmetric Gaussian wave package. And these two guys here, those coefficients, it's related to the polarization. I mean, it's related to the direction of the propagation. And here it's a plane wave, it's like a pulse, okay? Just to say that to solve that in time, you use the Pauli matrix and the Euler identity. For those that give lectures in quantum mechanics, you can find out this in chapter 3 of Sakurai. So, with that in mind, we start a Gaussian wave packet, we evolve in time, and see what is happening. And the first paper that we published about this subject was this PRL, where we took advantage of this model that I just described here, and we explored the Zeta-Bewegung effect. So the Zeta-Bewegung effect was predicted in the 1930s for Erwin Schrödinger, and it's pretty much related to the trembling motion and oscillation of, 4 minutes. For 20 or for 25? Okay. 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 So just to say that the hetero-bilayers effect, it's this trembling motion and oscillation in some observable. And in this PRL, we observe that if you set your system with certain pseudo-spinel component, in the absence of any external field, your average position will oscillate, but the amplitude is too low. But in the situation where you close the gap, I mean, when you have a Dirac-like excitonic band structure, the amplitude of those oscillations, it's at least 1 order of magnitude, and the time the time scale for this oscillation is in the order of 5 picoseconds. It means that unlike all the previous paper concerning hetero-bilayers in graphene, bilayer graphene, different materials, yes, maybe should be a platform to identify hetero-bilayers. So with that, in that paper that I just mentioned, in that time we didn't pay attention for the situation in the case that since our band structure is just shifted around 0, even if we started a wave packet in the gamma point, I mean with no momentum, your wave packet will travel. And more than that, it go to exhibit some elliptical cyclotron-like orbit. But I have to emphasize that no magnetic field was applied. That was really surprised. And the larger this sigma is the wave packet width, the larger is the wave packet edge, the larger will be the radius of the trajectory. And we realize, and okay, maybe should be some threshold for that. And I go to show in few slides using a Heisenberg equation of motion. Oh, I jumped too much. Okay, maybe I jumped these movies. And change other system parameter like the twist angle, you also go get those orbits. And when you increase the twist angle between them, we also see a large trajectory radius, elliptical shape. It's not so good. And here we show that we showed it similar, but when you close the gap, there's this situation here. You have a Dirac-like Moire excitons. There is no more cyclotron orbit, it just goes straight. And all those results were obtained in the absence of, I mean, without taking account any initial pulse, momentum is equal to 0. Okay, okay, I go to switch that. Look at this one, it just goes straight, the center of mass. And to predict this, we tailor expand those starting by model. As you can see, it looks like a like a continuum model with a certain anisotropy, since me minus and me plus are different. And moreover, when I look at, okay, this looks like Hashba-like term. And this is nice because it gives us some connection with those cyclotron-like orbits, because we didn't apply no magnetic field. And in our case, this Hashba coefficient is related to the Moire superlattice period. And by writing down Heisenberg's equation for the center mass, the average position, and derive 2 times, decouple the equations, we finally can have our solution for X and Y average position. And what gives us some sign change here, explaining the anisotropy. So it means that the solution clearly presents an elliptical motion, whose the period is like that, depend on this delta that is related to the difference between VA and VB. And here is the semi-minor, semi-major ellipse X. So some statement concerning that is, you see that even if I take T2 equal to 0, this is third nearest neighbor. I wrote second, I just realized that this third nearest neighbor. This guy will be equal to this one. It means that it describes some circular trajectory. So it means all the eccentricity comes from the third nearest neighbor. And to confirm that, I plot the band structure, just taking account T naught and all of the hopes, and you get some trigonal warping-like effect. Moreover, I have to say that the nice thing about this work is that I realized that any kind of material that can be written, the Hamiltonian can be written like a anisotropic Dirac-like with certain break inversion symmetry. Due to that, you go to present those cyclotron-like orbits. And moreover, you can tune the size of the elliptical trajectory with our Hashba-like parameter. So to confirm all those predictions, use Heisenberg equation and our split operator wave packet propagation. Those dashed lines correspond to our prediction. And here you can see that for wave package larger than 1,000 angstrom, the analytical solution match really, really nice with the numerical calculations. And one more thing, we derive once the average, and you get some feelings about the group velocities, just to say that some spin polarization along y direction, and it's go to 0. I mean, I just go to jump because of my time. Just more comments. Just a final comment on that is we got some elliptical orbits for those Moire excitons without taking any initial momentum for the Gaussian wave packet, and our predicting using a continuum model and the Heisenberg equation of motion match perfectly. The larger is our Gaussian initial Gaussian wave package. And just to give some taste, working more on that, we have some results. This is in preparation, where we add some additional confinement, since that we have a gap or a Dirac-like when you apply a perpendicular electric field. And we got those confinement states analytically, and also some wave function confirm that you can add those additional trapping for those Moire excitons. So with that, I want to thank you for your attention, and again for the opportunity to give this talk.
Thanks for the talk. Now it's time for the questions. No question? I have one. So you have compared your results, so the results, the analytical and the numerical results. Mm-hmm. But what can you say about the experiments? So, yeah. So can you?
If I go back a couple of slides, there is one experiment where they pumped some light and got some ring-like shape as this one, like this one, for this situation. Okay. This is the most close result that I can directly compare. And I know that because it was one of the questions of the referee, and we look a lot, and we wrote this in this paper, is why I know.
Okay.
Okay.
Okay, thank you. Yeah.
Hi, Diego, very nice talk. Okay. So I remember you had a slide when you had the exton on the bilayers, mm-hmm. where you had the two bands on the two layers just shifted a little bit from each other. So my question, the
motivation part?
Yeah. So my question is, when you have the hybridization between the layers, and if the hybridization can be strong, how's the picture changes? I mean, then there will be hybridization.
Yeah, you mean about the orbital hybridization, and in principle, all those, as I mentioned at the beginning, all those how do you say that? Renormalization and reconstruction is already in the DFT. And after that, they was fitted, and the fitted parameter is included here. See? I mean, I just say that all that should be in the DFT before coming to the fitting and get our. So it's there. All the hybridization, all the reconstruction, everything are there. But of course, you're going to have a bunch of bands. Here are just close of 2 bands, a 2-band model, a 2-band model. For spin value, yes.
More questions? Yeah. Okay. Okay.
If I understand well, the plot of the beautiful like wave functions for the average position, right?
Mm-hmm. The center of mass.
So the results just can control the position of the wave function for better. Well, how much they are localized at the system?
I mean, yeah, it will be confined around that because this is the center of mass, yes? As I show in the video, they just tremble. It's quite hard to see if you can see in the movie. It's there because in all those cases, I didn't give any initial momentum. But it was surprised that it described those cyclotron-like orbits without any magnetic field. It's just because when we wrote similarly to Hashba-like term, it looked like that. It's like has some pseudo-effective magnetic field, but there is not.
More questions? So we thank Diego again.